Yeah, so the students used to complain that my Cal 3 class was too much work. And that's when I would give them 8 mini exams. They had to do them. There was no options, right? So you can imagine it would be pretty intense to have to continually do that all semester long. But again, I find myself having to state, you know, these problems are designed to make you think in a different way. It's going to be a problem that I haven't shown you how to do, and I want you to think through it. And I talked to a few students about this. You know, the whole idea is to try and make you a better problem solver. This is what it's all about. It's about when you are in the real world, there's not a textbook you turn to. You know, you have to go off of your own abilities to solve problems. And that's what I'm trying to get you all to do is you know, take a problem, sit with it for a day, think about it, think about it, think about it. Because in like the problem where I gave you the arc length was 4, like at some point you had to realize that means you needed to solve for the upper limit of integration. You had to figure out what, you know, you needed the interval of time that gives you a length of 4, if that makes sense. But that should take some thought because I've never expressed the problem to you that way. So, all right, your next mini exam, I don't think I'm going to give you till after spring break because I want you to focus on the midterm. So don't expect anything anytime soon. All right, so I was going back, and I usually don't rewatch my lecture videos, but I don't know if you remember I made a comment about making my daughter breakfast or something in the video. And I told my daughter, I was like, hey, you know, I was talking about you today in class. She's like, yeah. And so I brought up the video to show her, and then it was right near this part. And I just listened to myself, and I was like, man, I don't think I made it make sense. I don't know. I used the wrong language a few times. So I want to be very clear on this particular line right here, which was like the main result from last class, which is the gradient of a function, which is just a vector that is formed by taking the partial derivatives of the function. The gradient dotted with u is a unit vector that you're pointed in that direction. Okay, so if you take that right there, by definition, this is the directional derivative, which gives you the slope of the tangent line as you point in a certain direction, the direction of u, right? And what I said was that is, at the end of the day, since this is a unit vector, the magnitude is 1, this turns out to be the magnitude of the gradient. And I think in class I said the magnitude of the directional derivative. This is the directional derivative. It's equal to the magnitude of the gradient vector times cosine of the angle between these two vectors. And so what we said is that in order to make this as big as possible, we have to have that angle be 0, which means that your gradient vector and your direction you're pointing in, those angles, that angle has to be the same, 0, the angle between them, which means that your gradient vector, the direction of u is actually the direction of the gradient vector. They're the same direction. And that was the main result. So I just want to be clear on that. That's how we maximize the directional derivative, by making the angle between u and the gradient vector 0. Okay, moving on. So we went through that. We finished class. I think I gave you an example to work out on your own, which was, I think, this one. And then we're going to start, continue in that section. This is going to wrap up real quick. We come up with a formula here. And I want to remind you that we've seen a formula like this before. If you go back in your notes, come on, I wonder why that's closed. No. If you go back in your notes, we had a formula for finding the equation of a tangent plane to a surface. So we said, and go back in your notes, you can find it. It said if z is some function of x and y. All right. So if we have a surface, that's like, I'm thinking 0 for 3 this semester, I think. Okay, so if we have some surface, right, and we want to know the equation of the tangent plane at a particular point on that surface. Does anyone remember what the formula is? It was
a times x minus.
Okay, so this is the formula for a plane in general. right? This is a general equation of a plane, right? But the plane that would be tangent to that surface at a particular point was the partial of f with respect to x at the point x naught, y naught, then x minus x naught plus partial y with partial of f with respect to y at the point x naught, y naught, and then y minus y naught. Is this in your notes somewhere? Yeah, okay. And then this was the one that I told you is always -1, right? -1 and then z minus z naught, blah, yeah, like that. Okay, so that equation I already showed you. I said just remember this is always -1. The a is this partial, the b turns out to be that partial, and then the c is always -1, so long as you are looking at z equals a function of x and y. So as long as you could take an equation that has x, y, and z in it and solve for z, then here's your formula, right? Now today, the formula is going to be more general, all right? So we're going to generalize this formula to the scenario where we have a surface, right? But we're not able to isolate z. We can't get z equals a function of x and y. So an example of that would be, you know, x squared plus y squared plus z squared equals 9. That would be a sphere, right? That'd be a sphere of radius 3, because we've seen that equation before. This has 3 variables in it, but you can't solve it for z unless you take a square root and do a plus and minus, so then you'd have 2 separate functions, right? So in the case like this, can we still talk about a tangent plane? And the answer is yes, but our formula gets modified a little bit. What we do is we get all of our variables on one side of the equation and call the left side of the equation capital F of x, y, z. So we define a function of 3 variables to be the left side equals the right side, which is a constant, right? So this would be equals k here. Y'all see that? And in this case, the equation of the tangent plane to this surface at the point x naught, y naught, z naught. So you have to have all 3 points, or all 3 coordinates of the point in order to find the equation of the tangent plane, is this big ugly looking thing. All right, but just want to clarify. The last formula before this that I just erased, if we had a surface, right, and we wanted to find the equation of a tangent plane at a point, that little tangent plane there, all I needed to know was the x naught, y naught. And the reason I just needed to know x naught, y naught was because this surface is a function of z. I mean, z is a function of x naught and y naught. So as long as you give me x naught, y naught, I know where I am, and there's only one place I can be. But in an equation like this, where you're looking like a sphere, if you give me an x naught, y naught on the ground, then the output is up here and down here. So you could be talking about the point up there or the point down here. Does that make sense? So in order to find the equation of tangent plane, you have to give me exactly where you are, x naught, y naught, and z naught. Then I'll be able to know if I'm up here or down here. And then to find the equation of tangent plane, here's the formula. So does this look familiar? I mean, that's basically what it was in the last problem. Just we have this z in here now, okay? So we're taking the partial with respect to x still. So it's just like the other one. And how can I illustrate this? Let me give you a different example. Let's compare this one to this one, okay? So this is today, that was last class. If I told you right now to take everything to one side, then we'd kind of be like this is now, right? You'll see that? Everything to one side. Now, when I take the partial of this with respect to x, does that matter? It doesn't, right? So that's why in the previous formula, we could just look at the two variables, x naught and y naught, because z, when we took the derivative with respect to x, anything that had z in it was going to go to 0, always. That kind of makes sense? I think I'm confusing you. Let me just continue. All right, so this is still a partial with respect to x naught minus, or x minus x naught. Now here's the b, right? Partial with respect to y. Same thing as the last formula. Now here, this is no longer negative 1. Do you all see that? But do you see why it was in that case? Because mathematically, if you could solve for z, right? If you can solve for z, then if you were to move it over, you know that that z is the only z there, right? There's no other z's anywhere else. And it's negative now, isn't it? Because you moved it over. So if I take the partial of this with respect to z, what am I going to get? Negative 1 every single time, right? So that's why in the previous formula, this was always negative 1, and it was because we knew that we could solve for z and then move it over. Does that kind of make sense? So this formula is actually a more general formula, and if you can solve for z, then this formula becomes the last formula. Okay? All right, so it's really not a new formula. It is, but not really. All right, so we can see that the normal vector, right, the normal vector for this plane is that, that, and that. Okay, so there it is. And do you also recognize that the normal vector is the gradient vector? That's the gradient. And so the normal vector of this plane is the gradient vector of the capital F function. All right, let's do an example. Sometimes you just have to see this thing work out, and then you realize it's not that big of a deal. The formula looks nasty, but all right. So here we go. Find the equation of the tangent plane to the ellipsoid x squared over 9 plus y squared plus z squared over 25 equals 18 at the point negative 3, 4, 5. So we're assuming that since this was given to us, that if we replace x with this, y with this, and z with this, plug it in, we will get true equality. So that point does live on that surface. But we want to know the equation of the tangent plane. So first things first. We have an equation with x, y, and z. So we get everything with x, y, and z to one side, and we get any constants to the other side, which is already done, right? It's already presented to us that way. So this right here is our f of x, y, z, and then equals, and then this is our k. All right. Now, do we know x naught, y naught, z naught? Do we know the point that we're interested in? Yeah, it was given to us, right? So this right here, this is our x naught, y naught, and z naught. So what I need to do is I need to calculate the gradient vector for this capital F. So I need the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Those will correspond to my a, b, and c for my normal vector, the three components. So let's go ahead and just do that. What's the partial of f with respect to x here? So taking derivative of this with respect to x, this is going to zero out, that's going to zero out, right? Those two are going to zero out. And so derivative of that with respect to x, 2/9 x. Partial of f with respect to y, pretty straightforward, 2y. And the partial of f with respect to z is just 2 over 25z. Very clean derivative, right? Now, using the formula, we need partial of f with respect to x evaluated at this point, right? X naught, y naught, z naught, and then times x minus x naught, plus partial of f with respect to y evaluated at x naught, y naught, z naught, and then y minus y naught. I'm rewriting the whole formula. I don't know why, but I will. Naught, y naught, z naught, and then z minus z naught equals 0. All right, so this right here is just that, right? But plugging in for x, y, and z, those values. But this only has x in it, right? So I'm just going to replace that x with -3. Make sense? So what is that? Plug -3 in there. So I'll just write it. 2/9 times -3. Then let's keep going. X minus what?
Wait, shouldn't it be 2/9 x?
Yes, but I'm replacing x with, because now I'm going to the actual point that I'm interested in. So I replace it with -3. Then x minus what? Minus -3, so +3. And then plus, now I need my partial with respect to y at this point. Yeah, so this only has y in it. It just so happens. Next problem, I think it won't be this way, but this happens to just have y, so I'm going to replace it with 4. So 2 times 4. and then y minus 4 again, and then plus partial of f with respect to z, which used to be -1, but now it's not, and then 5 there, right? And then z minus 5 equals 0. Does everything make sense where everything came from there? Okay, now let's just clean it up. So this should be -2/3 x plus 3, let's see, plus 8 times y minus 4, and then plus 2/5 z minus 5 equals 0. So that right there is the equation of the plane that is tangent to that surface at that particular point. And I could clean this up, you know, if this were me trying to clean this answer up, I would multiply everything through by 15 to clear fractions out, and then distribute, and then, you know, yeah, whatever. But I'm just going to leave it like that. You happy with that? Okay. So let's just verify that we've done this correctly. I have a picture of the surface, the ellipsoid. Now, are you all very clear with the idea that this ellipsoid is not a function of x and y? That because, again, it wraps around itself, it's not like a blanket floating in the air. It's like a circle is in other classes. Circle comes all the way around, fails the vertical line test. This, in some sense, fails the vertical line test also. You have an input, x, y, goes to 2 places. But we can still find the equation of the tangent plane. So here's my ellipsoid. Let me kind of spin it around. That's the point, -3, 4, 5 on that ellipsoid. And we just calculated that plane. So if I have my computer graph it, that plane should be tangent to that surface at that point. Okay? So we just found the equation of that plane. Questions? All right, let's see. Oh, you know what? I think that was the only one. Oh, no. This is different. This is different. Find the equation of the normal line. Okay, so we've never done this. We've never talked about it. So it's time to talk about it. A normal line. So we have this ellipsoid, right? We went to a specific point. So that's the same ellipsoid. We went to that point and we found the equation of the tangent plane, didn't we? What we'd like to know now is if you have that plane sitting there, what's the equation of the line that is normal to the surface at this point? And that means, like, okay, so let's say my knuckle here is that point. Here, I'll even color it for us. There we go. So that's the point on the ellipsoid. My tangent plane's going through it. Then I want to know the equation of the line that is basically orthogonal to the plane, all right, but sticking through that point. So what's the equation of that line? That's called the normal line. So what do you think? What do you need in order to find the equation of a line, of any line? You need a point and a direction vector. So we go back to the whole idea of, all right, I need to find this good old guy from way back when, right? I need an initial point that I'll convert into a vector, and then I need v, which is a direction that the line is pointing in. So can somebody give me what r naught should be then? -3, 4, 5, right? I mean, this point is on the line we're talking about. So let's just use that as our r naught. And how about a direction vector? Can you give me a vector that points in the direction of that line?
Wouldn't it be the coefficients of the...
Yeah, it's, whoa. The direction of that line is also the direction of the normal vector for the plane, which is the same as the direction vector, or not direction, the coefficients that we got when we computed the partials, those partials. So I believe it was what, -2/3? -2/3, 8, and 2/5. And then I could put that together, right? All into one vector. So it would be like -3 plus, I don't know, minus minus 2/3 t. And then 4 plus 8t. And then 5 plus 2/5 t. So this is a three-dimensional line, right? It's three-dimensional. And if I graph it, it should pass through that ellipsoid at the same place that the tangent plane is going through, but it should be orthogonal to the plane. And that's what that picture is right here. So here's that same ellipsoid. We had that tangent plane. So we just found the equation of that blue line going through there. Make sense? Okay. So not a whole lot more to do there other than to recognize that you have this and have this. This is all, you've already computed all this. All right, and that does it for 11.6. And now we move on to 11.7. Maximum and minimum values. So we started talking about this last class. We had a problem where we saw that our partial derivative was 0 or something, and we were asking, like, is that like a maximum? And I said, we'll do that soon, and here we are, we're doing it today. So let's first start with review from Cal 1. So if you did the mini exam that was due today, you would have run into this a little bit within the exam. And that is, back in Cal 1, how do we find the maximum and minimum values of a function? Right? So let's see if we can recall this. I'm going to split the board into two pieces because there's two techniques. One of them is when, what? Huh? You okay? Okay. One of the techniques is the one that you learn first is this one, finding max and min of a function on a closed interval. So whenever you have a function on a closed interval, finding the max and minimum of that function is actually easier than if it's not on a closed interval, if it's on an open interval. So this one is going to be basically finding what we call local max and min of a function on an open interval. And the techniques were similar but very different. That doesn't make sense. Yeah, similar but not similar, but no? Okay. Similar but not at all alike. That makes perfect sense? Okay, does anyone remember how to do this? Like, I'll give you a specific example. If somebody gave you the function f of x equals x cubed minus, let's go with, let's go with 3x squared, and they give you that function on the interval 1, 4, and they ask you to find the maximum and minimum values of that function on that interval, how would you do it?
Take the derivative.
Take the derivative.
Plug in both of the endpoints and then find where it equals 0 and compare the values you get.
Find where what equals 0?
The derivative
Okay.
equals 0.
So what we did in Cal 1 is we first took the derivative of this and we found what we called critical points or critical numbers. And that's anywhere where the derivative is 0 or undefined. Then what we would do is wherever the derivative is 0 or undefined, we would take those answers and we would plug them back into the original function. And we would also plug in the two endpoints, and then we would just compare them. Say, okay, whichever is the biggest, that's where we have the max. Whatever's the smallest, we have the min. So let's just do that real quick. So we take derivative real quick. This is going to be 3x squared minus 6x, right? Take our derivative. Find our critical numbers. So set it to 0. F prime equals 0 means that 3x squared minus 6x equals 0. I can just factor this, pull a 3x out. I get two solutions, 0 and 2, right? So far I have two critical numbers. I also have to consider anywhere where the derivative is undefined. In this particular case, the derivative is a polynomial, so it's defined everywhere, so I don't need to worry about that. But just remember, critical numbers includes not only where it's 0, but where it's undefined. Okay, so we only have 2 critical numbers, and then we have 2 endpoints. So at this point, all we have to do with this closed interval method is take our original function and evaluate it at all 4 of these points. So it doesn't matter what order you do these in. And what we're looking for is where we're going to get the biggest number and smallest number. So 0 is easy, right? F of 0 is 0. And these are getting plugged into the original function. What's f of 2? Is that negative 4? Negative 4. F of negative 1? Negative 4 again. And f of 4? So 64 minus 16. 16 times 340. Yeah, I think so. 16. Sounds right. Okay. So what is the maximum value? What's the maximum value? 16. Okay. And the minimum value is negative 4, but it actually occurs at 2 different places, doesn't it? And so let's just confirm this with a graph, just so we can make sure we understand visually what's going on here. Does that method look familiar to you? The closed interval method? Okay. So if I do x cubed minus 3x squared, but we only do this between, what was it? Negative 1 and 4. Get out of here. Oh, is it doing it? No, I don't think it did it. Did it stop it at 4? I think that just adjusted my window. Okay, that's probably good enough. So between negative 1, negative 1's here, right? We're right there. Negative 1, we were at negative 4. So these are counting by 2's, so that's right. And then at 2, we were at negative 4 also, right? And then at 0, we were at 0. And then at 4, we were at 16, which is right there. Okay, so the maximum was this one, and the minimum was here and here because we're only looking between there and there, right?
You can change the domain in Desmos with the function itself.
Or just right in there?
Yeah, use curly brackets, and then use the inequality, like negative.
Oh, okay, negative 1,
x.
less than equal x, less than equal to 4. Wow, thank you so much. I knew there had to be something in there to do that. Appreciate that. See, I learned something today. We good? Okay, so how does that differ from the other method, which is to find the local max and min of that function f on an open interval? Let's just say that function again. But this time on, let's just go on the whole number line. Boy, those are some rough looking infinities. Let's just do the whole number line because this is a polynomial, so it's defined everywhere. So if we want to do this, what's the difference? What do we do?
We find the first derivative, find where it's 0 undefined.
Yeah, so we still do this. We figure out where that's that, and we figure out where the derivative is undefined. So these were called critical numbers, right? So we still find the critical numbers, which we already know would still be x is 0 and 2, right? Just like that. But now we don't have endpoints anymore. So at this point, what did you do? And I think this might depend on your the class that you had and the instructor that you took.
We found the end behavior.
Well, if it's a polynomial, I guess you could, right? Let me start showing you how I showed my class, and then we'll see if this rings a bell. The way oh yeah, because I know my method is way different than the book's method. So a A lot of you probably learned to do some sort of like sine table or something like that. I don't know. This is the way I teach it. I say, okay, once you get your critical numbers, you put them on a number line. Okay? And what that does is it creates a natural partition of your number line into 3 regions. Now what I do is I pick a test point in each region, and I plug the test point into what?
The second derivative.
Okay, so that's another way you can do it. That's second derivative test. This is the first derivative test. This way, we're still going to get the same result, but I don't have to calculate another derivative to do it. So I'm going to let me take a test point, -1, take a test point here, 1, test point over here, 3. So I have 3 test points, and these get plugged into the derivative. And the reason why is because when I plug -1 into the derivative, here's my derivative right here. Let's plug -1 in there. What would you get if you plug -1 in there? F prime of -1. Get 9? Right? You get a positive number. And that's all that matters to us. Okay? Is that this becomes a positive number. And that means that over here to the left of 0, my derivative is positive, right? Which means my original function must be increasing. And so what I always tell my class is just don't worry about pluses and minuses, just tell me what the result is. The result of plugging -1 into the derivative and getting positive means my original function is going up here. Then we plug in 1. When we plug in 1, we see what we get. Into the derivative, what do we get? Negative. So I get a negative number, which means now my original function is going down over here. And then I do it for 3, and it's going to go up again. We won't do it, but it goes up like that. So anytime you have a function that goes up and then down, and at that point you have a critical number, then you are going to have a local maximum there. Anytime your function goes down and then up, and that point is a critical number, then you're going to have local minimum. So here we would have a local minimum, or we'll say local max first. Local max at x equals 0, right? That's where it happens. And what is the actual value of the original function at 0? You plug into the original, you get 0, right? So we have a local maximum at 0, it spits out 0. Then we have a local minimum at x equals 2. And what is the original function's value at 2? I think we did that -4, didn't we? So with this, I think this was more work, which is why when you're in Cal 1, you learn this method first because it's easier to do. And then later on you learn this, and then there's like a second derivative test you can do. In my classes, let's just do this. Let's just figure out where it goes up and down, and then we can find our max and mins that way. All right, so this does not tell you about like a global maximum, does it? This just tells you what's happening locally. If you go back to the picture we had, it was like that, right? So all this method was able to do is identify those 2 points. That's all it could do, right? Where here, because we cut the function off, we could find the absolute maximum and absolute minimum of the function on that closed interval. But it had to be closed for us to talk about that. Agree? Okay, that's it. We're done with the review. Now, we're going to try and see how we can extend these ideas into what we are learning about here. So it turns out that when you have a surface, there you are. When you have a surface, you can have these undulations and stuff, and you can have little like local maximums and local minimums. You know, you might look at this right here and you might be like, oh, you know, it might be like, you know, that point right there looks like it's the highest point locally, right? It's not the highest point on the whole surface, but locally it's the highest. This down here looks like a local minimum. That looks like a little local maximum, a little local maximum. This one looks like a local maximum. But that one also looks like a global maximum, doesn't it? Like it's the highest point on the whole surface. This one actually looks like it might be a global minimum, like at the lowest. Now, how do we go about trying to find these, right? I mean, it's kind of the same idea as we had in Cal 1. We have a function, we were trying to find these points. Well, here's just a different picture. That one's a little easier to look at, but there you go. So we have, this is straight out of the book, I just photocopied the book. That right there is essentially like that picture there. We have the idea of a local minimum versus an absolute minimum, which would be the lowest. I just called it global, but we use those two words interchangeably. Absolute minimum or global minimum would be the lowest point on the whole thing. And then same thing, local maximum, absolute maximum. And then it goes in and it defines what these are. So I'll read through one of these. A function of two variables has what we call a local maximum at some point AB if, when we plug AB into the function, it's bigger than or equal to any other point on the surface whenever x, y is near AB. So it's like if you look, you plug in that point AB and you look around on the surface, everything is below you, right? Smaller than you. As long as you're just looking in this little neighborhood, you're the king of the mountain, right? You're the highest point on the hill. Where that would be a local maximum. Local minimum is the opposite. It's like you plug in some point AB, you look around you and everything around you is above you, locally. So you're at the bottom of the pit, so to speak. Now here's the important thing. Right here, this theorem, which we're not proving, we're just going to take it. If your function, your surface, has a local maximum or minimum, if it does, and the first order partial derivatives exist, so you can take the partials of the function, if those derivatives exist, then you're guaranteed that the partials are equal to 0 there. So we have to really understand what this theorem is telling us. If you have a point that is a local maximum or minimum, let's just go with maximum. So let's say you have a point where that is locally the highest point, okay, locally. Guaranteed both your partials are equal to 0. That means the partial in one direction is flat and the partial in the other direction is flat. I think last class we were talking about this, right? And well, you seemed interested, right? So you asked, when we had one of our partials equal to 0, is that enough to say we have a maximum? Actually, we need them both to be 0 for us to be able to say that. So if we have a local max, we're going to have both partials be 0. Now, you have to be a little careful with the logic. Does this theorem say that if we have this to be true, let's say both my partials are 0 in both directions, does that guarantee a maximum? Yes. Or minimum?
You know, both our partials in either direction are 0. Does that mean every directional derivative at that point will also be 0?
Great question. No. That's not guaranteed. This theorem says that those two are. Now that would be a great thinking question though. Okay? What is the definition of, let me make sure I get the question on camera because this is a great question. This says if we're at a local maximum or a local minimum, these two partials must be 0. Partial in the direction of x, partial in the direction of y, right? The question is, does that mean all the directional derivatives are 0? Like in every direction, is it 0? Yes or no? So, do you remember the formula for the directional derivative?
I'll have to look at it.
Okay, all right. The directional derivative of our function, f of x, y.
The unit vector?
Yeah, we use that unit vector, right? And so it turns out like we have to have a unit vector. We call that unit vector AB, didn't we? And then we said that the directional derivative is just a partial of f with respect to x at the point plus b partial of f with respect to y at the point. You can look back in your notes. This is the formula. I squeezed it in here. So now you tell me, if we are at a local maximum or minimum, this theorem guarantees that these two have to be 0. What can you then tell me about the directional derivative? It would have to be 0 also. Because look, this has to be 0, doesn't it? And that has to be 0. And therefore the directional derivative would have to be 0. See, because your directional derivative is just made up of both partials and then scale them. But these scalars don't matter at all if these are both 0. right? So your directional derivative will be 0. So when you initially answered that, or asked that question, I think I said no, didn't I?
Yeah.
But it's the order, that's what I was trying to say before you asked the question. So the order in which you state things is important. If I tell you that the directional derivative, so let's say I tell you I'm at a point on a surface, and the directional derivative in every direction is 0. Does that mean you can say that you are at a local max or min?
That just could mean everything's flat.
It could mean everything is flat, right? So when we look at theorems, the order is important the way it's stated. This is saying if you're at a local max or min, then you're guaranteed that the partials are 0. This does not say that if the partials are 0, you are at a local maximum or minimum. There's logic in here, and I think this is the best explanation I can do it. Have I shown you this one? Yeah? If you live in Texas, then you live in the United States. Everyone agree with that? Can you reverse this, though? Can you say if you're in the US that you're in Texas? You can't, right? You can live in New York, and right? So when you have an if-then statement, if it's if this, then this, you cannot reverse it. You're not allowed. And so that's what I'm saying here. It's saying if we're at a local max and min, then these are 0. That does not mean that if these are 0, we are at a local max or min. The theorem has to be read this way. Now, some theorems you can read both ways. And in your studies, you might see this. X equals 2 no, this is not going to work. Yeah, I'll just do it. X greater than 0 and so this is one statement. If I say x is greater than 0 and x is 2, all right, that is if IFF, if and only if. Have y'all seen that before, if and only if?
Yeah.
These go both directions. So whenever you see an if and only if, it's not them like trying to say, yeah, this really is strong. It means both directions. But I need to read this because this is actually not right. I need this. I need the and x greater than 0 on this side. Sorry. Okay, so now it'll work. Do you agree that if x is 2, then x squared is 4? Yes? Do you agree with that? And x is greater than 0, you agree with that? So if I say x is 2, then this is true and that's true, yes? Now, go the other way around. If I say x squared is 4, is that enough to say that x is 2? No, because x could have been negative 2, right?
It says x is greater than 0.
But I said x is greater than 0 also. So if both of these conditions are met, can you go that direction? Yes. If I take that off, this is incorrect. You would have to say, if this, then this. That would be correct, but it wouldn't go the other way. Does that make sense? So the logic here is very important. Anytime you see a theorem, if it says if this, then this, you cannot reverse the statements. All right. So now, with all that said, that was a good discussion. I like that. We have what we call a second derivative test. So just like in Cal 1, we had ways to determine whether or not you were at a local max or min. We have this very nice test for surfaces that allows us to tell us whether or not we are at a local max or min. And you can read through this. You look at it, first time you see it, you're like, what the hell? Okay, what we're going to do is we're going to start with a function, all right, a surface, and we're going to say to ourselves, let's say that the partials are 0 at some point. So at some point we discover that our partials are 0. That doesn't mean we're at a max or min, right? We just said that. Just because your partials are 0 doesn't mean you're at a max or min. But here's how we can test to see if it is. What we're going to do is we're going to call the point AB where we get these partials to be 0, we're going to call those critical points. Just like before, remember in the previous problems we took the derivative, we set it equal to 0, we said we call those critical numbers. Well, anywhere where our partials are 0, that's going to be called a critical point of our function. And then what we're going to do is we're going to calculate this thing called capital D. And capital D here does not mean derivative, all right? It's just what we use, okay? Someone picked it, it's capital D, all right? And we're going to compute the value of capital D. And what it is, it's the second partial of, with respect to x twice, times the second partial with respect to y twice, minus the partial with respect to x, then y, that squared, subtracted. We do this calculation, and then we have three different things that can happen. All right, we're going to do an example, okay, but this is the formula I'm going to use. If this number right here, D, that we calculate, turns out to be positive, there's two things that could happen. So if it's positive, and then not only do we have D as positive, but this piece right here is also positive, then you are at a local minimum. All right? Understand? That's the way the formula works. If the whole thing is positive and that piece is positive, you are at a local minimum on your surface. Now, if the whole thing is positive but this piece is negative, just that piece, then you are at a local maximum. If this thing is negative, if you calculate this and this thing is negative, then you are not at a local max or min. You are what we call a saddle point. Okay, so this right here is called a saddle point. So we're going to be doing some partials and second partials to do these problems. There was something else I wanted to say. One way that I remember this is that in order for me to be able to say I have a local max or min, I need D to be positive. So I need my test to be positive in order for me to draw any good conclusion. And then this piece right here, if it's positive, I have a minimum. And think about second derivative. Remember second derivative was concave up and down? So this is saying, like, kind of saying your second derivative has to be positive, which is like this, concave up, and that would be a minimum, wouldn't it? And then this one, second derivative is negative, is like that, and that corresponds to a maximum. I don't know if that helps, but D has to be positive for you to be able to use that. If D's negative, the test failed, and basically failed. And that doesn't fail, but it tells you you don't have either one. Okay. Let's do an example. Here's a surface. Now I'm showing you the picture, which is kind of cheating because you kind of can look at the picture and know what's going to happen here. But we're looking at that right now, and we're saying, hey, does it have any extreme values? Extreme values means, does it have any local maximums or any local minimums? Does it? Are there any little hills or valleys on this surface? Now, from the picture, does it look like we do? Does it look like we have like a hilltop, like an ant pile? Or like a little valley? Does it look like we have that anywhere?
There might be a saddle point.
There might be. It looks like a saddle in the middle, right? Like right here. Because like in one direction, it looks like it's doing this, but in the other direction, it looks like it's doing that, which is like a saddle. Doesn't that look like a saddle? But I don't see anything that looks like, you know, like this, right? Where we have an obvious, like, local maximum anywhere. But without the picture, we wouldn't know that, would we? So let's go through the work. Okay, so the first thing I'm going to do is say this. If I have a local maximum minimum, if I do, right, then I know that the partials have to be 0 there. So I'm going to find out where the partials are 0. Those would be good candidates for where I might have a max or min. So you're going to first start by taking the first partial. Partial of f with respect to x. What is the partial of f with respect to x there? Negative 2x. Okay, now I want the partial of f with respect to y. Just 2y. Now remember, if we have a local max or min, it's going to be where these are 0, right? If we have a max or min, then these have to be 0. So I'm going to just look to see where that happens. So right now what I'm doing is I'm trying to find my critical points, which means I'm going to set my partials equal to 0. Do you see how this is very similar to what we did in Cal 1? We set the derivative to 0. We're setting the partials to 0 to try and figure out what's going on. So now, here, take that, negative 2x, set it equal to 0, and there's one solution there, x is 0, right? And then here, take 2y, set it equal to 0. There's only one solution, y is 0. So what you're trying to do by finding a critical point is trying to find a point, an ordered pair, A, B, that makes this true. So can somebody give me a point that makes that true? That makes both of these statements true at the same time?
0, 0.
0, 0, right? If my x is 0 and my y is 0, then these two will be 0, won't they? So this is my critical number. This is my critical point for this surface. This is the point that I'm interested in. Something interesting is happening at 0, 0. I don't know what yet, but something interesting is happening. Does that make sense? So now I've got to go calculate capital D. So capital D is the second partial of f with respect to x twice at the point AB times the second partial with respect to y at the point AB minus the partial of f with respect to x then y at the point AB, and then all of that squared. Okay, so that's our formula. That means I need to take second partials, right? I need to calculate all these second partials, and then once I get them, plug in 0, 0. So let's do our second partials. What would the partial of f with respect to x twice be? -2. Partial of f with respect to y twice? 2. And then we never did this one. What's the partial of f with respect to x then y? 0. Right? 0. So we're basically taking this one and then differentiating with respect to y, which gives us 0. Make sense? Okay, now plug it into the formula. Now what you're going to find here is that when we go to find this, right, we're supposed to plug in 0, 0, right? But do you see that our second partials are all constants? In this particular problem, that's what happens. So this point actually becomes irrelevant because our second partials don't depend on anything, right? They're just constants. So this right here is -2. This one right here is +2. And then minus, we said this was 0 squared, and that turns out to be -4. And that means our capital D is negative, which means what? We have a saddle point, right? Now, where do we have the saddle point? At 0, 0, right? Now, I just said that 0, 0 had no impact on this, right? But this is the only point where our first partials are 0, right? In order to have a max, if we're going to have a max or min, that's going to force our first partials to be 0. And since this is the only point, this is our saddle point. So this means we have a saddle point at 0, 0, which is what the picture looks like, right? At the origin, it looked like we had a saddle point. What do y'all think? Are there some similarities between this and what we did in Cal 1? Do you kind of see a little bit of it? And I also said in the Cal 1, we did closed interval first, right, in Cal 1, and then we did open interval because it was harder. Here, we're actually doing it reverse. We're doing, like right now, this surface, I have not given you any domain restrictions, have I? Like I've just said, look at this surface in every direction forever. After we do this, we're then going to restrict the domain. And it's going to be kind of like the closed interval method from Cal 1. And in this class, the closed interval method is harder than this method. So that's why we do it backwards here. Am I making any sense? Okay. We'll have to do it for you to appreciate it. It's going to be a lot more difficult if I restrict our domain. All right, that one was too easy. Don't you think those partials were just too easy? Yep. Yeah. So let's try something a little more challenging. That one's a little more challenging. So I'm just going to go out in the hallway and grab a drink. While I'm out there, find partial with respect to x, then y, and then go ahead and get x twice, y twice, and then xy, because we're going to need all 5 of those, aren't we, for this? All right, so go ahead and do those. That should only take you about, what, 30 seconds? 36 seconds? 40 seconds? Those are the 5 derivatives I got over there. Everyone just check yours. Anybody disagree? We're all good? Okay, so what first?
Well, find the critical point.
Yep, so we're going to work with those 2 first, right? And we're going to find our critical points. So that means I need to figure out where that's 0. I also need to figure out where that's 0. All right. Things are going to get interesting here. I'm going to go ahead and write these down. A little different than last problem, right? So I just set both of those partials equal to 0, and there's a problem here because you cannot solve this uniquely. Like, you can give me an infinite number of solutions here, can't you? I mean, there's an infinite number of answers here, and there's an infinite number of answers here. So I guess what I could say is you could solve this for y, couldn't you? Like, I could solve that for y, but it would be in terms of x. And then you could solve this for x, and it would be in terms of y. So that's really, you're not going to really get an actual x and y coordinate. You're not going to get an a and a b. But there's something else I can do algebraically that might help. What you got?
You have a system of equations here. You need to find where both of these equal 0. Where
That's
both
right.
of these conditions are true.
That's right.
So we have 2 variables and 2 equations we should be able to solve.
We should. We should be able to solve because we have 2 equations and 2 variables. I think what you're thinking is like using some sort of like elimination or substitution or something like that?
Yeah.
Okay, so normally when we say we have 2 equations, 2 unknowns, you know, we can solve and do a system of equations. Those are usually linear equations. That's where you use like matrices, and if you wanted to, like Gaussian, well, elimination and substitution, those have always been linear equations. I agree with you that we should be able to solve, but the techniques are not going to be the same because these are nonlinear equations. Am I making sense? Because you've got y cubed and x cubed. As soon as you have cubed or squared or something like that, all the stuff you learn in college algebra with elimination and substitution kind of goes out the window. You can't set up a system. All right? So we can't really do that. But look, aren't they both equal to 0? So don't they both have to be equal to one another then? Right? If this has to be 0 and that has to be 0, then they have to be equal to one another. So why don't I do that? If I do 4x cubed minus 4y equals 4y cubed minus 4x, then I might be able to do something here. Let me see. What can I do? What can I do?
Distribute up to 4 and get rid of it.
Yeah, can we just divide everything by 4? Okay, let's divide everything by 4. Gone, 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 gone. Okay. What else?
You could add x and y to both sides.
Yeah.
All
Okay.
x on one side and y on the other.
You could do x's on one side, y's on the other. I'm not sure how that would go. Can I try? Yeah, I mean, I might let you mess with that a little bit. I'm going to do this, though, and just see.